Welcome back to AI.Code.Cast, everyone. Today, we're going to be diving into a classic coding puzzle. It's one that pops up in technical interviews all the time, integer division, but without using division.
Yeah, it's a real brain teaser. It really makes you think differently about like how division works at its core.
For sure.
Yeah.
Like, imagine you're in a coding interview, right?
Mm,
The pressure is on, and
mm.
they ask you to divide two integers. Easy peasy, you think?
Right.
And then, bam, the interviewer hits you with, but you can't use division, multiplication, or modulo operators.
Oh yeah, that's when it gets fun. It's not just about knowing the language anymore. It's about like really understanding algorithms and how to solve problems creatively.
Absolutely. So we've got to find the equation of two integers,
Okay.
but we can't use the tools we normally would. So where do we even start?
Well, I think sometimes the best way to tackle a tough problem is to start with the simplest solution, even if it's not the most efficient one.
Okay, so what's the most basic way to, like, do division? If we can't divide directly, maybe we could just keep subtracting the divisor from the dividend.
Yeah, like a brute force kind of approach.
Exactly. We just keep subtracting until we can't subtract anymore. And then, like, however many times we subtracted, that's our quotient.
You got it. It's definitely a valid way to do division.
But I'm already seeing the problem. Like, what if the numbers are huge? This would take forever. Imagine subtracting 1 from a million over and over again.
Right, it would be super slow. So we've got to think, how can we optimize this? How can we take bigger steps instead of subtracting one at a time?
Okay, bigger steps. So we need to subtract multiples of the divisor, right?
Hmm.
But how do we figure out what those multiples are? We can't use multiplication.
That's the tricky part. We need a way to find the largest multiple of the divisor that we can subtract without going negative.
Hmm, largest multiple.
Think about it. How can we scale up the divisor quickly?
Scale up, could we maybe use doubling? We could double the divisor until it's bigger than the dividend, then step back to the previous value.
You're on the right track. That's the idea behind an exponential search. We use the power of 2 to quickly find the biggest chunk we can subtract.
Okay, so let's say we're dividing like 93706 by 157.
Yeah.
We start doubling 157, so we get 314, 628, and so on. We keep going until we get a number bigger than 93706,
Right.
which would be 160768. So the previous double, 8384, that's the largest multiple of 157 that fits.
Exactly.
And we doubled 157, what, 9 times to get there. So 2 to the power of 9, which is 512, times 157, that gives us 80384.
Nice observation. So you subtract that from the dividend, and you're left with 13322. Then you just repeat the process, finding the largest multiple that fits within 13322, and so on.
Okay, I like where this is going. It's like we're doing division, but by finding these big chunks and subtracting them. But before we get too excited, there's something we haven't talked about yet. Negative numbers.
Oh, yeah, you're right. Negatives can get tricky. What if the dividend or the divisor or both are negative? How do we handle that?
I'm not sure. It seems like dealing with negatives would add, like, a whole lot of extra complexity.
It could, but there's actually a really clever way to deal with this. What if we converted everything to negative numbers right from the start?
To negative numbers. Wouldn't that change the answer?
No, not at all. We handle the sign of the quotient separately based on the original signs. Converting to negatives does two things. First, it gives us a bigger range of integers to work with, so we can avoid overflow issues. And second, it actually makes the calculations simpler.
Wow, that's pretty neat. Converting to negatives actually makes things easier. I would have never thought of that. So we've figured out how to do repeated subtraction. We even have a way to deal with negative numbers.
Yep, we're making good progress.
But I'm curious, this whole doubling strategy, where could that lead us in terms of, like, actual implementation? Think about how computers work with numbers.
Okay, doubling and computers.
Wait a minute, are you talking about bit manipulation? Can we maybe use bit shifting to do all this doubling and halving?
Bingo. That's where we're headed next. We're going to dive into the world of bit manipulation. And trust me, it's going to change the game for this problem.
I can't wait to see how it all comes together. Listeners, make sure you join us for part 2. We'll be getting into the nitty-gritty of how bit manipulation can supercharge our integer division algorithm. All right, welcome back to AI.Code.Cast. So last time, we kind of set the stage for how to divide integers without using actual division. And we even tackled negative numbers.
Yep.
But now it's time for the really cool stuff, right? Bit manipulation.
Exactly. Remember how we were doubling the divisor over and over to find those big chunks we could subtract?
Yeah.
Well, bit shifting lets us do that way more efficiently.
Right, like shifting a number one position to the left is the same as multiplying by 2.
Yep.
So instead of actually multiplying to double, we just use the left shift operator in binary.
Exactly. So instead of writing out like divisors, divisor 2,
Right.
we would just do divisor 1. That shifts it left by 1 bit.
Oh, okay.
And we can do the same thing to keep track of the power of 2, right? Like have another variable, maybe call it power of 2.
Okay, I'm with you.
And we just keep shifting them left, both of them, until the divisor gets bigger than the dividend.
Right, and then back up to the previous values.
Right. And those previous values, that's the biggest multiple of the original divisor that fits inside the dividend.
Okay, that makes sense.
Right.
But how do we actually, use that to do the division?
Well, we know that biggest multiple, so we can subtract it from the dividend, right?
Right.
And since we know how many times we doubled, we know what power of 2 to add to our quotient.
Oh,
So we'd have a quotient variable started at 0, and then in our loop, as long as the dividend is bigger than or equal to that shifted divisor.
we subtract and we add the power of 2 to the quotient.
Exactly. We're basically breaking down the dividend into these nicely sized pieces. And after each subtraction, what do we do? How do we get ready for the next step?
To get ready for the next step, we've got to go to the next smaller power of 2.
Yeah.
So we should shift both the divisor and the power of 2 one position to the right.
Yep.
Kind of like undoing one of the doublings.
Exactly. We use the right shift operator,
Yeah.
1, to cut their values in half.
This is so clever. By shifting bits, we're basically doing the same thing as finding those subtractable chunks, but it's way faster for the computer.
Right. It's a really cool example of how understanding binary and bit manipulation can make your code way better. And the best part is we're still not using any multiplication or division.
Oh, yeah. Speaking of things we're avoiding, didn't we say there was something tricky about right-shifting negative numbers?
Yeah, you've got a good memory. But it turns out that's not a problem for this algorithm.
Oh, phew, good. So we can shift those negatives without worrying about getting the wrong answer. But you also mentioned another way to do this, right? Binary long division. I'm really curious about that.
Absolutely. That bit manipulation method we just talked about, that's what people usually use. It's really efficient.
Right.
But understanding binary long division, it's like a whole different way of seeing how division works with bits. Plus, it's a good mental workout.
Okay, I'm up for a base 2 challenge. But before we get into that, let's just quickly go over what we've learned about bit manipulation so far.
Good idea. So we've seen how bit shifts can replace multiplying or dividing by 2, which helps us find the perfect chunks to subtract.
And we also saw that starting with everything as negative can stop those overflow problems and just makes the calculations easier.
Exactly. We've covered a lot. So now that we've got a good grasp on bit manipulation, let's switch gears and explore binary long division.
Welcome back to AI.Code.Cast. It's the final part of our deep dive into integer division without using division. We've covered a lot already. Repeated subtraction, bit manipulation.
Yep.
And now it's time for something that sounds kind of scary. Binary long division.
Yeah, I know it sounds intimidating, but it's really pretty cool once you get the idea.
To be honest with you, I haven't really thought about long division since grade school.
Yeah.
How does it work again?
Okay, so let's say you're dividing 1234 by 5, like the regular way, base 10.
Right.
You start by looking at the leftmost digits of the dividend, 12, and you ask, how many times does 5 go into 12? It goes in twice, right?
Yeah.
So you write a 2 above the 2 in the dividend.
Okay, yeah, I remember that.
Then you multiply 2 by 5, get 10, and subtract that from 12, leaving you with 2. You bring down the next digit, 3, to make it 23, and then you just repeat the process. But how do we do that in binaries where we only have zeros and ones?
Right, yeah, that's what I'm wondering.
Well, it's actually pretty similar. You go from left to right, bit by bit, but instead of asking how many times does the divisor go into, you just ask, does it fit into this part of the dividend, or is it too big?
So it's just like a yes or no question each time. Either it fits or it doesn't. That's kind of neat.
Exactly. And that's what makes binary long division so elegant. If it fits, you subtract it. If not, you move on to the next bit. And you can do all this with bitwise operations.
Okay, I'm starting to get it.
Yeah.
But there's still something bugging me. We're supposed to be avoiding multiplication, right?
Right.
And long division involves multiplying the divisor to find those partial quotients. How do we get around that?
That's the clever part. Because we're in base 2, we can basically do multiplication by just adding repeatedly. And we can do that with bitwise operations.
I see. So we're sneaking around the actual multiplication by being clever with the bits. This is amazing. But honestly, it does seem a bit more complicated than the bit shifting way we talked about before.
Yeah, you're right. Binary long division is really cool conceptually, but maybe not the best choice in an interview when you're under pressure.
Right.
That bit manipulation method, that's usually more efficient and easier to get right.
So should we even bother with binary long division then?
Oh, absolutely. It might not be the go-to solution for this exact problem, but it gives you a really deep understanding of how division works at the bit level. And that kind of knowledge is super valuable for any programmer.
I agree. Sometimes it's about the journey of learning different approaches, not just finding the fastest solution. So after looking at all these methods, from basic subtraction to bit manipulation and even binary long division, what's the big takeaway for our listeners?
I'd say the biggest takeaway is just how powerful and versatile bit manipulation can be. Once you understand binary and bitwise operations, you can make your code way more efficient and elegant.
Totally. It's like you're speaking the computer's language, you're getting down to the bare metal. And for those of you who want to keep pushing yourselves, here's a thought. How would you adapt these techniques to handle fractions or division by zero?
Yeah, that's a great challenge. Thinking about those edge cases will really cement your understanding of what we've talked about today.
And that's it for this deep dive. Keep coding, keep experimenting, and we'll see you next time on AI.Code.Cast.